See, one thing on this handout, listen, on this handout, a couple of things that are not quite correct. It's kind of old, so the technology they were using to create the handout wasn't quite as capable as more modern software. But the concepts are very good, so I've not found the time to upgrade the handout. The dots here are a little bit large. Just remind yourself that the dot represents one dot, like one tiny little infinitesimally small dot. This particular dot, as we talked last time, is located at -2, 0. And that means that this function f, the function, remember, is a long list of xy pairs. One of those xy pairs is -2, 0. This open circle is kind of large, but it represents the fact that there's nothing located at that spot. So you would never write this, well, you can in the scratch area, but it's not official notation. So I just kind of remind myself that there's nothing there. My little dots here. Question. Okay. We've done that. This also is a little bit weird. The limit, typically you'll put this x approaching 2 plus underneath the limit sign. For some reason this software put it out to the side. Not super critical, but it's better to write it the way the AP test writers write it. So, okay, we're finding the limit as x approaches -2 from the positive side. So like we talked last time, that means I find x equal -2. That's right here. I'm supposed to choose an x value that is slightly positive of x equal -2. So I'm going to pick, say, this point right here. And now I note that that y coordinate is about 1.5. So I choose an x coordinate that is closer to x equal -2, like this. That y coordinate is 2. I pick an x coordinate that is even closer. If I continue that pattern, I'm zooming in to this area, and I can see that every time I pick an x coordinate that is closer to x equal -2, the y value becomes closer to becoming exactly 3. The y value never does equal 3. It just gets closer and closer. Question. Again, remember, don't copy the procedure at all. Make sure you can figure out how I'm thinking and it's making sense to you, like you can feel that it makes sense. Then you'll be fine. Okay. These two, I pick an x coordinate that is close to 0, but slightly to the left. So that means I'm picking, say, this x coordinate. The y coordinate there is about 1/2. I pick an x coordinate that is closer to 0, and then closer to 0, and then closer. So I am zooming in this area. And I notice that as I do that, the y coordinate is getting increasingly closer to 0. The y coordinate never goes to 3 until I get to exactly x equals 0. That would be doing this. F of 0 is equal to 3. Questions about any of it? Perfect. If I'm finding x approaching 0 from the right, I would be zooming in this area in blue. I would note that every time I pick an x coordinate that's closer to x equals 0, the y coordinate is going to be closer and closer to y equals 0. Okay, this one I don't think we got. I can't remember. Did we talk about this last time? Okay. So x approaching 0, you shouldn't look up here at all. You should simply look at these two. And because they are the same, the overall limit will be the same. So, non-existent. They're different, it's non-existent. Questions? Okay. do this whole page, and I'm just going to walk the room, and then we'll check it together. Do the whole page. Stop me if there's anything you want to talk about. Just do that whole page. Feel free to work together. Feel free to stop me.
Yeah, so on number 5, so it's coming to, so if it's coming to 2 here, I'm trying to, it's coming lower and lower, so that's it's getting
So first part was right. Here I am. Next coordinate that is slightly negative. So I now we take the next coordinate that's closer to 15. So I move this. The negative is because here the white point is.
It would be the same as the 2 left, right? If it's here, it's still giving it larger.
You did the right answer.
Yeah, and then almost to the left.
This is definitely where would you put it? That's a wide one.
Oh, it's 6. So okay, so you're talking about X here. I'm trying to find the Y. I'm going here.
Then you differentiate off the dot. Starting correct. So now we want to make our X coordinate closer to 2.
I know I had more than 1.
It's got to be one of the dots. Where is the dot? That was successful. We went to the next coordinate 4 against the we're approaching 2 from the positive. So we're paying attention to the trend of the white. So I want to get closer. Yeah. So now it's like the white
And I guess I'm But I have a phone. So I get to go home for like 25 minutes and come back. Because like it's a foreign class. Third period.
What do you think?
This oh yeah.
Choosing an export that is opposed to zero. It needs to be on the negative side. So I have my function, I've got all these dots to fit. It really doesn't matter which one you pick as long as it is on the left side of the thing. So you're going to a dot that's on the left side. So let's go. So your thinking kind of begins with and then you say, well, what's the white part? Now you just pick an export that is kosher to zero, point to a dot that's kosher. And you pay attention to white, which is about, I do decimal, this thing is about 0.2. And now I pick an export that's kosher, about 0.1. And now I just observe it. And every time I pick an export that's kosher, it's telling me exactly the white coordinate is comparing to kosher. Oh, really? So this line is. It doesn't jump back up here until I go past. Wait, no, yes. Alright, so let's do this one. So where would you start with this? That's very good. You're trying to zoom in higher, and you see all the dots, and you say, okay, every time I move closer to the dot that has X equals 0, both white coordinate are getting closer and closer. So I have a dot right here. What white coordinate are very close?
Yeah, so you can see yourself doing so much.
The X coordinate is really close to 0. Now I need to see another dot that's even closer. Perfect. Move closer to X equals 0. White coordinate is closer. So this limit is 3. I wouldn't ever go to here. I just want to get So for the overall limit, you never want to go to here. You always want to go to Okay, just a reminder, since it's only our third day, every time I say your name, make sure you put down the tally marks when we're having the class discussion. When I'm working one-on-one, that's kind of different. So, Kate, I want you to vote with your hand. So this means 0. You don't show everyone, just show me. 1, 2, 3, 4, 5. It makes it so I can check the room pretty quick. So we're just going to go down this list really fast. So jump over to here. So show me number 1. Can you show me your answer? Checking the whole room. So if you're doing this, give yourself 3 tally marks. Okay, show me number 2. Go. Show me number 2. Show me number 2. Checking the whole room. If you're doing this, give yourself 1. Go to number 3. This promotes comfort with big numbers, because everybody wants to have a big number for an answer. That wasn't a very good joke. If you're doing this, give yourself 3 more points. So, okay, when you find this one, remember, don't look up here. When you're finding this, do not look up here. Look here. Because these two are different, the overall limit is non-existent. So when the left limit does not match the right limit, the overall limit is non-existent. If the left and right limits match, then the overall limit is the same. Question? Awesome. So moving on. Just say it out loud, please. What's 5 said?
3.
Louder?
3.
Questions? Just wave at me if you have a question. Anyone needs me to talk through it? Number 6 said?
3.
So that makes 7, 3. Let's go over here. Number 5 said?
2.
Number 6?
2.
2. 7 is also 2 then. Okay. Stop and talk for a minute about this. Okay, I mentioned that this kind of a couple days of discussion is we are discussing limits and continuity. So to this, because they go together. So far we've just been talking about limits. So continuity, you need to put a couple things in your notes. You need to make sure you have it memorized. Okay, it's really easy to memorize the general idea of what continuity is. A function is continuous as long as you can draw the function without ever lifting your pencil. So if I can draw all the dots without ever lifting my pencil, the function is continuous. It's a pretty easy definition. Never had a student who had a hard time remembering that. So, function's continuous if you can simply draw the function without lifting your pencil. Again, that's one that just comes intuitively. Everyone always remembers that. Associated with this, they will require you on occasion on the AP test to identify by name the type of discontinuity, like something that makes the function discontinuous. For example, up here, I obviously cannot draw this function without lifting my pencil. I have to draw this dot, then I have to come up and draw all of these, and I have to lift my pencil again to draw this dot, etc. So this function is continuous in places, but it is not overall continuous. Anybody need clarification on that? Like along here, the function is continuous. I can draw all of those, but not all of it. Okay, the 3 types of discontinuities that you have to memorize. So number 1, we don't have an example of it on this page. I'll show you one in a minute. It's a discontinuity you've seen in other classes, the vertical asymptote. So vertical asymptote is a type of discontinuity. You can't draw a function. Here's an example. So I'm drawing the function, it's continuous here, and I have the vertical asymptote. I have to pick up my pencil to get to the other half of the asymptote. The function is continuous everywhere except where the vertical asymptote is located. That's this type of discontinuity. Question? Okay, second type is is a removable discontinuity. Okay, somebody last period gave a good way of remembering the idea of removable. They said, oh, it's like here, where I'm drawing all of the dots. Everything looks great, the function is continuous. But right here, a dot has been removed. It's gone. And then it's up here, and then I just go back to drawing the function again. So this idea of where there's just a missing dot, but the rest of the function looks pretty normal, that's a removable discontinuity. The fact that the dot is up here doesn't really matter. That's just part of the removable discontinuity. This function, where was it? Oh, here. Here's another example of removable, where I'm drawing a continuous function, suddenly there is no dot, and then I keep drawing the function. That's a removable discontinuity. Even though there isn't a dot anywhere here, it doesn't matter. It's still removable. We need clarification on that. Please, Charles.
So for it to be continuous, it has to be all dots that are filled in.
Correct. If there are any missing dots, the function will not be continuous. Perfect. Please.
What if it were like, so on this function on the left here, like if it's coming and then it goes like a parabola kind of to like a straight line, if that were filled in, would that be continuous?
So like if I did this,
Yeah, exactly.
then in this region here, the function is continuous. Because I can draw all of this portion of the function without lifting my pen.
So I didn't know it changes like it's.
Yeah, the abrupt change is something else we'll study later. But as far as continuous, this is definitely continuous. That's a really good question. It's very good. Anybody else? Well done, Josh. Okay. The other thing you need to memorize about removable, okay, a removable discontinuity occurs when the left and right limits are the same, but different than the value of the function. So that's what's happening here. The left and right limit are both 0. We saw that on this page. Just a word. The left and right limits are both 0 here, but the value of the function is 3. That's a removable discontinuity. We see it again here on this one. The left and right limits are 3. So this dot is open. The value of the function, f of 2, would be undefined. Mostly just semantics, like people just felt like they were subtly different, so they chose different words. Otherwise, kind of the same idea. So, point for Josh. There we go. Cool. Okay, so removable, left and right limits are the same, but the value of the function is different. That's a removable discontinuity. The last type you have to memorize is a jump discontinuity. So jump actually,
Not like with removable.
oh sorry, removable left and right are the same.
Okay.
Like here, these two are the same, but the value of the function is different. So the value is the middle. Left and right are always what's happening infinitesimally close to the middle, but not at the middle. Good question, Justin. Okay, last type is a jump discontinuity. That's when the left and right limits don't match. So jump discontinuity, left and right limits don't match. This is an example of a jump here, where the left and right limits are different. We did that one over here. So the left and right limits are different. That causes a jump at x equals 0. Please.
Does this just not have horizontal asymptotes?
Dawson Ellis, right?
Yeah.
Perfect. And horizontal asymptotes have a similar name, like vertical asymptote, horizontal asymptote. But a horizontal asymptote is not a discontinuity. So it has a similar name, but don't lump it in with these at all. So a horizontal asymptote, as Dawson pointed out, would look something like this maybe. Where the value of the function is getting close to some y coordinate, but this function is still continuous. So, good question. Yeah. Perfect. Okay, next thing. Any questions at all on this side of the sheet? We didn't go through checking all of them. We got through most of them just to make sure there's no questions. Here's the last answers. Questions on any of that? Which one, 8 and 9?
On the first one.
Over here.
Yeah.
So the way you think of it is, point for Justin, I go to x equal 2, and now I'm right at x equal 2. So I'm looking exactly at x equal 2. And I look everywhere in this picture where the x coordinate would be 2, and nowhere is there a dot whose x coordinate is 2, hence undefined. So I look here, I'm looking to see if there's a dot whose x coordinate is 3. I find it here. That y coordinate, sorry, 0 for x, 3 for y. Question, Justin, please.
Does it matter if we say undefined and non-existent? Like, does it matter which one we choose to say?
Sorry, my voice. I've never seen them have these types of questions on the written section, so it's always in the multiple choice.
Okay.
So you just pick their word, and they'll use non-existent or undefined.
Okay.
If you were to happen to write it incorrectly, maybe they would not give you the point. I'm just not sure. So I try to get you to use the right words. Carson.
Can functions have multiple line values and x values?
The definition of a function is for every x, there's only one y, so you won't see that. They will give you problems that involve what are known as relations, where you can have that, but it's not common. So, good question, Carson. Anybody else? Perfect. Okay, I'm going to grab a drink real quick. Flip it to the other side. Okay, here we go. Okay, first thing, again, you're not copying the procedure, you're making sense of the idea. The first thing you want to do is say, okay, look, they're giving me a function f, so that's exactly the same as what we've been doing. This is a function called out, okay? The only difference is this function is defined graphically, so the dots, the xy pairs, are represented graphically. Here, for this function, the xy pairs are computed with formulas, but it's still just a bunch of dots. We just don't see them. Are you with me? Okay. So, for answering these questions, your logic is exactly the same. There's just a slight adjustment you have to make in how you think about the problem, and I'll show you. First of all, I'm trying to prep you again for the AP test, not just for this homework assignment. So now that we're doing limits involving formulas, I have a little recipe that you'll want to always follow. I found that it is extremely helpful in getting through any limit problem on the AP test. Here's the recipe. You'll want to memorize this. you first check to see if the limit is x approaching infinity or negative infinity. So you want to memorize this recipe. It makes a big difference. So just checking to see if the limit is x approaching infinity. This particular problem is not that, so we don't have to worry about what we would do if this were the case. I'll show you that later. In tonight's homework, there are none that do this, but they will be on the next assignment. So that's the first step. Just check if the limit is approaching infinity. Second step, you look to see if it's possible to factor and divide. Okay, we won't encounter any problems that require this today either, so we won't worry about the details, but I do need you to get memorizing it. So, the third step is to simply check the left and right limits. And we will do that right now. So we don't have a limit as x approaching infinity or negative infinity. We don't have any case where we can factor and divide because we don't have rational functions, we don't have fractions. So we're going to check the left and right limit. So over here it says, go find the limit from the left as x approaches 3. Just as a reminder, with a piecewise function, this is your index. This is telling you what x coordinates are valid. These are the formulas that you use to find the y coordinates. So just like before, just like when we were doing the graphical example, I need to pick an x coordinate that's a little bit more than 3, like 4, 3.1, whatever. So I look at my index. I've got to figure out which formula is used when I have an x value that is bigger than 3. So I just want you to say it together and see if you're all following my thoughts here. Are you going to pick the top, middle, or bottom? Say it. Bottom. Good. So I pick the bottom formula, and I think to myself, okay, I'm choosing an x value that is bigger than 3. I'm going to give kind of a detailed example just to make sure no one gets lost. So let's do this. Let's go bottom formula. So I plug in an x value that is bigger than 3. Well, 4 is bigger than 3. So 2 times 4 is 8, plus 1 is 9. Now I pick an x value that is closer to 3. 3.5. Now, I do all of this in my head. But yeah, please, Justin.
So why did you use the 2x plus 1 even though we decided on like the...
So I said the x value is bigger than 3.
Okay.
This formula gets used if the x value is in between 0 and 3. This formula gets used if the x value is precisely 3.
Yeah.
Oh, this is the one I use when x is bigger than 3.
Okay.
Keep going.
Well, so like why are we using 2x plus 1 instead of the x is greater than 3?
Oh, my bad. Sorry, I misunderstood the question. Perfect. Good job, Justin. This isn't a formula. This is specifying what x's get plugged into this formula.
Okay.
So it's saying if you have an x that's bigger than 3, like 4, 5, 6, or whatever, then this is the formula you use to find the y value.
Okay, so depending on what your x needs to be, is okay.
Perfect. This is the x's you're using. This is the y values that you
They
find.
correspond to it. Okay.
Perfect. Anybody else? Cool. So let's see. 2 times 3.5 is 7. 7 plus 1 is 8. Now I pick an x value that's even closer to 3. 3.1. Oh, this would be 6.2, so this is 7.2. I do all of this in my head. I don't write it down. You don't have to write it down either. You simply have to recognize the pattern. That if you were choosing x values that were getting closer and closer to 3, this formula would be producing numbers, y coordinates, that are closer and closer to 7. We don't want to talk about any of that.
Basically, we just need to like figure out the number that it's going to be close to, but never get to.
Perfect. Because with a limit, you are limited to X values that never become 3. They just get closer and closer from the positive side. Perfect, Justin. Awesome. Finish this real quick. I'm going to walk the room. Stop me if you want to talk about any of it. Do 2, 3, and 4. Go. Feel free to talk to each other. Feel free to stop me about anything.
Yeah, but it's saying it's in between zones. So I mean, so 2 squared and 4 minus 2. Now let's go to. No, I think you can go closer to 3. So 2 parallel. Oh yeah. I was about to say I'm actually not walking around.
I just have one box, just to make sure. If you keep going, it's fine. Okay, here we go. Just say it loud, please. What did you get for number 2? Say it. Louder? Okay. Just raise your hand if you got 7. Show me. We got 7 here. So point for the whole room. I just try to see how we're doing. So, about a third of you students raise your hand. Question? Cool. This one's easy now because I don't look up here. I just look at these two. And I notice that these two are the same, so this limit must also be 7. Okay, show me on your hand what you got for number 4. Show me on your hand like this. Show me what you got for number 4. Some people weren't quite there yet. Everyone give yourself 2 points. So when the x-coordinate is exactly 3, the y-coordinate is exactly 2. Question? Okay, new idea here. It doesn't say on the sheet, but we need to practice this for the homework and the AP test. This means yes, this means no. They will give problems like this on the AP test. They won't outline it for you. They'll just give you a function like this, and they'll say, show that is the following function continuous at x equal 3? They'll ask if the function is continuous. We don't have a picture to look at, so we can't really see the whole, this kind of thing. So we're looking to see if there's a vertical asymptote at x equal 3, a removable discontinuity at x equal 3, or a jump discontinuity at x equal 3. We just pay attention to the limits and the overall value of the function. The two limits are the same, left and right, so there isn't a jump. Just go like this if you need me to talk through that again. Okay, left and right are different, so no jump. However, the overall value of the function is different from the left and right limits. That's a removable discontinuity. So this function would have a removable at x equal 3. It's not continuous at x equal 3. If the function were continuous, the left limit, the right limit, and the value of the function would all be the same. That's the definition of continuous. So, we need to restate anything.
So please, if that number 1 and 2 were both 7 and number 4 was 7, they would not be removable, right?
Correct. If 1, 2, and now 3 is just, these two, so that's really easy. 1, 2, and 4 all the same, function is continuous. 1 and 2 different, jump discontinuity. 1 and 2 the same, different than 4, removable discontinuity.
So in the AP test, it would be like just to do this top thing, and then you have to draw this to prove why.
Perfect. No, Josh said that perfectly. I've seen AP questions that literally say, prove that this is not continuous at x equal 3. And what you have to do is you write down the left limit, you write down the right limit, you write down the value of the function. You say, hey, they're not the same, therefore remove them. Perfect. Anybody else? Awesome. Next one. Okay, finish this sheet real quick, and then we'll check it. So do all of this. Go. Stop me if you want to ask about anything. Josh's names again. Just to you talk it. I'll play this a little short one. So the pattern really is plugging in smaller numbers and see what happens. The shortcut is to say, well, we know we want x to be close to 3. So let's just see what happens. So 3 squared is 9 minus 2. Okay, don't stop there. You're just going to think to yourself, well, what if the number I put in wasn't exactly as it is? It's just a tiny bit. Well, this wouldn't be 9 anymore. But this would still be really close to 7.
0.5. I think you put 5 in music. What are you doing?
You can stay upside down. Essentially, although you do need to keep track of the fact that it's not exactly one, it's just close. Like, again, don't do it as a procedure, make sure you're thinking about it. So I'm thinking, okay, I need to have an x5 that's a little bigger than 1. So I'm thinking, okay, just like Sydney said, if I plugged in exactly 1, 3 times 1 would be 3 plus 1 would be 4. Just an infinitesimal amount larger. 1.00001. This would still be really close to 3. This would be really close.
So I thought it was if it's discontinuity.
And then the safety requirement. So this one's the easy one because it's just x is exactly 1.
I guess. I don't want that at least.
The limits you really shouldn't just plug it into the code because you got to remind yourself when you know when it's closed. Exactly.
And so,
Right. We're limited undefined because this is the definition. And in this definition, nothing defines what y coordinate we get when x is -2. Limits, they use the word non-existent. Function values.
you get one for that. Yeah. I do 1 minus 2.
All these dots are pairs.
Yeah.
This is what happens.
How do you like?
X equals 1.
Oh yeah, it has to be discontinuity. I don't think it would be
So it's the right and the left limits don't match. Yeah. And I'm pretty sure it's
Now the next one is lads.
You just plug in 3.01 and see what our numbers are listed.
You guys get 11 for 9. But it's a lot faster if you don't. You just go 2.99.
Isn't it? It's greater than
It's usually 9.
Hey, look up real fast. We only have about 5 minutes, so just try to keep moving a little bit. Just say these answers. So, any questions here? Please.
How do you find out what discontinuity is? Like,
Oh,
no.
gotcha. So, removable discontinuity occurs whenever the left and right limits are the same, but the value of the function in the middle is different. A jump occurs whenever the left and right limits are different. So this one has a jump. This one has a removable.
Yeah.
Oh, good question, Sydney.
And then how do you find if it's a vertical asymptote?
The vertical asymptote is when the limit left and right is approaching positive or negative infinity. So none of these will have that today, but that's what's happening. Say number 9, please. Say it. What's the answer? Number 10? 5. So that makes 11 non-existent. 12? Question? Okay, 13. Say it, please. 3. Say it together, it helps. 14? 3. 15? 3. And this one's undefined.
Would that just have a open circle?
Very good. So hey, point for Justin, also Sydney, because it relates to her question. So here we've got left and right limits are the same. The value of the function in the middle is not there. So yes, this would be one of those functions where there's just a missing dot, and that missing dot doesn't show up anywhere else. It's just gone.
So it's
Been removed.
It's
So
removable at like x equals -2.
that's how you say it. Because elsewhere we haven't really analyzed. So there is for sure at x equal -2. Good job, Sarah. Okay. Everybody look at me. A couple things about the homework. So this is the homework packet for tonight. This will kind of vary depending on the assignment. Sometimes I give you a single sheet with problems that you will do in your own paper. Just put it in your 3-ring binder. Sometimes I find that to be a little bit, I'd actually like to do that all the time, but I can't afford the paper. But sometimes I feel like it is important to have the problem on the same paper as the work. That's this example. I do that often with graphs. So you do the work in this document tonight. You don't need to use separate paper. There should be plenty of room. I'm really, I would just say, OCD about not having enough space, so I work hard to give you plenty of space. Look up. Okay, every homework assignment I give you, I think without exception, maybe there's 1 or 2 exceptions, the answers are in the back. Okay? Now, you got to be really careful. Listen, talked heavily the first 2 days about how the whole idea is to make sense of the concepts, not just do the work. You cannot just kind of fake your way through the homework because the answers are there. You're digging your grade. Okay? You're just headed for disaster. Only use the answers to confirm what you have already done. When you check, you're like, oh, it's different. Turn back to the beginning and just ignore the answer. Don't work backwards. It does not work in this class. It will cause you all kinds of problems if you're like looking at the answer and going, oh, well, that looks about right, and then you change yours. Okay. Don't do it. A little out of time. If you remind me next time, I'll tell you a pretty funny story about that. So, look at me. Okay, it's pretty straightforward. Now, I am asking you to do quite a bit of writing on this assignment. There's a reason. I don't like busy work. I hate it. But on the AP test, the written section, you have to learn to use the right notation. So, this is all blank, right? It says analyze the continuity using limits. That's because you're supposed to do what we've been practicing. You're supposed to find the left limit, the right limit. Once you have the left and right, the overall is easy. And then you're supposed to find the value of the function. Then you do what Sydney's been doing. You look at it and say, okay, what kind of discontinuity does this have? And you write that down. You look at the answers, that's what the answers show you. It's left limit, right limit, overall. Practice writing them. Not kidding. Like, it will feel a little tedious, I get that. But on the written section, you must remember how the notation looks, otherwise you don't get points. So, okay, do your best. When you come back, I'll ask you to homework next time.
Thank you.
Thank you.
And if it was that, yeah, I did. Dude, my A-days suck. I have like all my
Good job. You're fine.
So